So hey, thanks for coming. I'm Josh. So before I jump in, I want to see what we promised in the event invite, and then I will give you the agenda. So in the event invite, we promised no machine learning experience assumed at all. So I know we have a mixed group, so what we will do is the first hour, I will assume you know very, very little. And for people that have a lot of experience, yeah, I hope that's OK. And in the second half, we'll go a lot faster, and I'll show you some more advanced examples. So hopefully you'll all get something out of it. We have a small group, so if you have any questions, just interrupt me whenever. Here are the slides from today. They're actually from a conference in Montreal about 2 weeks ago. They're like 80% the same thing, but they have all the important links, so you don't need to take notes. You can just go to that link. There's a PDF. You'll get everything you need. If you have a laptop today, awesome. You can try TensorFlow 2. If you don't, you can make a friend next to you, and you'll still get something out of it. You can try all the code at home. So it's bit.ly ICSE 3. All right. So basically, I only have 1 or 2 boring slides that actually introduce TensorFlow. But here's the goal, and we're going to get through as much of this as we can. So the goal is to install TensorFlow 2.0. Then we will talk about machine learning basics, and we'll do this in a very, very low-level way. So I'll show you linear regression from scratch. And the reason we're going to do linear regression from scratch is it turns out the ingredients of linear regression are basically the same, surprisingly, as the ingredients for a deep neural network. After that, we'll do deep neural networks, and we'll do it in 2 different styles. One you may have seen before, the beginner style, if you've used a library called Keras. And the other, the expert style, or the research style, you may have seen before if you used a library called Chainer or PyTorch. And we have both of these in TensorFlow 2. It's great. And then the cool advanced stuff we'll fly through at the end at warp speed. Here's my only boring slide. So what is TensorFlow? So TensorFlow is an open source library. It's coming up on 4 years old. It was released by Google in 2015. By far the most important thing about it is the user community. And we're going on about 2,000 open source code contributors, which is nuts. So that would be like 30 times the number of people we have in the room right here from all around the world, which is incredible. Anyway, 2.0 is currently in alpha. 2.0 is a rework of TensorFlow to make it much easier to use. TensorFlow 1 was exactly what you would have wanted in 2015 if you were an engineer at Google and your problem was training neural networks at scale. It wasn't what you necessarily would have wanted, although it was still way better than a lot of things that were available at the time if you were a PhD student and you wanted to dive into deep learning. TensorFlow 2 is the best of both of these worlds. So it's just as fast as 1, it's just easier to use. The beta version of TensorFlow 2 is either releasing now or tomorrow morning. And I hope the website is still working. If not, we're going to have to scramble a little bit. And the final should be in a few months. I'll come back to this stuff later. So for people that are entirely new to machine learning, I have some bad news, and that's that, so what is deep learning? Deep learning is a subset of machine learning. It's a very technical, specific subset that really means representation learning. Deep learning is the wrong place to start your machine learning career. It is a niche technical area. You need to start your machine learning journey by taking a basic machine learning class, learning about k-nearest neighbors, decision trees, training data, testing data, evaluating models. Deep learning means doing machine learning with neural networks. So because of that, it's a little bit difficult to introduce quickly, but I will do my best. You won't understand all this, but if you get something out of it, cool, and you can dive deeper later on your own. This is a cool website you can play with right now if you have it. You can follow along, or you can try it at home later. It's called TensorFlow Playground. If you search on Google for TensorFlow Playground, or the URL is playground.tensorflow.org. And this is a neural network running in the browser, totally in JavaScript. I will show you a much cooler thing done totally in JavaScript in a second. By the way, TensorFlow 2, you typically write your code in Python, and that's what we'll do tonight. TensorFlow 2 has a C++ backend that makes your Python code much faster. We also support JavaScript and Swift. Anyway, neural network running in the browser. This is going to be a classification problem. And the goal is to find a line to separate the orange dots from the blue dots. And what we have here, this isn't quite a neural network yet. This is a mock-up of a single neuron. And what we have to the single neuron is there are 2 inputs. Here they're written as x1 and x2, but what they really mean are the x and y coordinates on this screen. Not shown is a grid, and you can imagine that this image on the right is divided into maybe a 100 by 100 grid. And what we're really trying to do is classify every little square on that grid and say, is it orange or blue? And the nice gradient there is based on the confidence score of the classifications. And it's not actually smooth, even though it looks smooth there. So it's a grid. We have the x and y coordinate of each cell. And the goal is to try and find a line that will separate the blue dots from the orange dots. And here, using a single neuron, which is a linear model, it's taking a linear combination of the weights and inputs, we can find a line. You can think about a single neuron as something that's able to draw a line. And we're in 2D space. We have two inputs, so we can draw a line like this. The problem is, if you have a nonlinear data set, and I'll show you how you draw the line in a minute. If you have a nonlinear data set like this, there's no way to draw a line to separate the data. So if we try and train our little neuron here, it can't do it, because obviously you can't draw a line to separate the blue dots from the orange dots. If you've taken a machine learning class, and by the way, all the TensorFlow examples we're going to look at in a sec are way easier than this. Deep learning has a lot of heavy concepts, but the code is really, really simple. Anyway, I just want to show you a very little bit about the concept side. So the problem is our little neuron can't separate this data. But if you've taken a machine learning class, and there's no way to know this if you haven't, unless you're really, really bright, you might know that there's a way to separate that data with a linear model. And it's a math trick. You can do something called feature engineering. All you have are the x and y coordinates on the screen. But you can add a new feature, z. And you can do this manually. And the trick you might come up with is if you look at the data, you realize that the red dots are always farther from the origin than the yellow dots. So that means if you create a new feature, z, and the value of z is x squared plus y squared, because we're squaring the data, it's always positive. And the magnitude of z is always larger for red than yellow. And that transforms the space to look like this. And now we can't draw a line, but in three-dimensional space, we can draw a plane to separate the data with a linear model. And we can do that in TensorFlow Playground by adding new features, x squared and y squared, which is close enough. But now if we train our linear model, it can separate the data. It's finding that plane. And that's really cool. The challenge is, the problem is to do this, we had to think. And we had to do math, and we had to do feature engineering. And feature engineering, coming up with smart features to separate your data, works great when you have a toy data set like this. But it doesn't work well when you have real data, like images, video, text, sound. So what we need is a way for feature engineering to happen automatically. And that's what a neural network does. So we'll keep our complicated data set, but we'll still just use our simple input features. But now what we'll do is add a single hidden layer. Now we have a neural network. This is a neuron that you can think of as a little logistic regression unit. Here's another one, another one, and another one. The idea here is that our first neurons are looking at the x and y coordinates. But our second layer of neurons is looking at features computed by the first layer of neurons. So you can think of they're looking at some input times a value, or they're looking at combinations of inputs. And what happens is when we train this model, even though we just have the x and y coordinates as input, now with these simple features, we automatically found a new feature that let us draw a plane to separate the data. So neural networks can automatically find these features for you. And this is extremely valuable because when we're working with real data sets like images, the only features we have are the pixels. And we need something that can learn a hierarchy of features. So that's like the deep learning the hard way. You can actually see, by the way, if you take a deep learning class, this is a visualization that I made earlier. And what we're looking at is this is a data set of moons. And we're actually watching how the neural network is twisting and bending the space as it's coming up with features to pull the moons apart so it can draw a line to separate them. And it's really, really cool. But anyway, the programming side of these neural networks is way simpler. So we'll do one hard exercise, which is linear regression from the ground up. And then we will start actually writing neural networks. And this is going to take like 20 lines of code. The neural networks will take 5. But let's just do it the slow way first so you can see every piece. So if you bring this up, so here's a link you can go to. I'm going to walk through this. And you can follow along if you want. So bit.ly tf-workshop1, tf1. All right, so let me show you what's going on here. Nice. All right, that was easy. This is like the easiest university Wi-Fi to ever sign into. I really appreciate it. So just so you know, has anyone used Collaboratory before? OK, so 30%. For people that haven't, this is a huge takeaway. You're going to love it. Totally independent of TensorFlow. Collaboratory is like the best thing since the microwave. And what it is, have you used Jupyter Notebooks before? OK, some people haven't, so let me introduce what a Jupyter Notebook is. A Jupyter Notebook is a Python environment. It's open source. It's free. There's two ways to run Python. Well, there's several. One is you can run it from the command line, Python, or you can use your favorite IDE or whatever. One such sort of IDE is called Jupyter, and Jupyter runs in a web browser, and it connects to your Python backend running on your machine. And the reason we like Jupyter Notebooks is there's two types of cells. The first cell is called a markdown cell, or I'm not sure what they call it. It's a text cell or a markdown cell. All cells can be edited and run. The way you edit a markdown cell is you just write some markdown. And to run it, you can hit Shift, Enter, press play, and it renders it. The reason we like this is it means you can put graphs and stuff in line with your code or text. So it's awesome. It's like self-documenting code. The other type of cell, as you might guess, is a code cell. And here you just write regular Python, Shift, Enter, it will run it. So Jupyter, which is what you're looking at, is a front end, and it's connected to a Python backend. What Colab is, it's a free Jupyter notebook that runs in the cloud. There's no way to pay for it even if you wanted to. It's from Google Research. It's good for education and demos. What's nice about Colab is it has a free GPU, which is why we want it for deep learning. So in Colab, here's how you use it. The reason I'm saying it's free is there's no sale here. Please don't mind Bitcoin on it. But because it's free also, the GPU is limited to 12-ish hours a day. So this is good for training medium-sized models. If you're a grad student, you can get a ton of use out of this. And the GPUs are very, very fast. NVIDIA, they're super fast. Anyway, to use Colab, just so you know what we're looking at, the link we have is actually on GitHub. So what Colab is doing here, that short link that I gave you, if you delete the colab.research.google.com and you put github.com instead, this is just a Jupyter notebook on GitHub. And the URL I gave you just opened it directly in Colab, just for convenience. You can always get out of Colab if you don't like it or you're tired of it. You can just do file, download as Jupyter Notebook, and you're back on totally open source. Anyway, in Colab, the first thing you can do is hit connect. And what you're doing is you're connecting to a Python backend. It's a virtual machine running on Google Cloud. It's transient. It might get deleted, so don't put important data in here. It's your own VM, so you have root access to it. And in all of the notebooks, the only boring thing we have to do is install TensorFlow 2, which is an alpha. TensorFlow 1 is installed here by default, along with other deep learning frameworks. So you're going to have to run this a lot. It takes like 2 minutes. But I want to teach you the new way of doing things so you don't waste your time learning the old way of doing things. So we'll run that, and we'll install TensorFlow 2. By the way, any command that starts with a bang or an exclamation, that's a shell command. So you can do bang ls, bang rmrf star if you want. Other really amazing things about Colab while that's installing. Strangely, hidden inside the table of contents method, there's something really useful. So if you go view table of contents, you find this, which no one cares about. But if you go to code snippets, everyone cares about this. So let's say you wanted to download something from Colab to your local machine. You would type download, and here's basically code you can copy and paste into your notebook and run that will do the thing you want, which is awesome. And you can use this if you want to connect Colab to Google Drive, if you want to install your other favorite deep learning library, if you want to learn how to put graphics inside your notebooks, it's all there. So this is like super, super helpful. Colab also recently added a file browser. You need it, if you want to upload and download files easily, you can do it through the file browser. So you totally don't need this for TensorFlow. Anything you do in Colab will run locally too. This is just super, super awesome. The way you enable a GPU is edit notebook settings, strangely, and then you can select a hardware accelerator. Don't use TPUs right now. They require code changes, but they won't in the near future. But GPUs will accelerate most TensorFlow operations out of the box. All right. We have installed TensorFlow 2. I'll go super slow for now, and then we'll go faster. The first thing we're doing is TensorFlow. You can think of it as a Python library. We're importing it. And it plays nicely with NumPy. So the first thing to do in linear regression, we're going to do y equals mx plus b. And we're going to create some random data, and then we're going to try and find the best fit line. So this I will move through quickly. But what we're doing, oh, damn it. What we're doing, this notebook already has output, which I don't want now. So you see I have some graphics from the last time I ran it, because I uploaded those to GitHub. So I'm doing edit, clear all output. One more thing with Colab, if you get it into a weird state, you need to reset it, you install the wrong library, you can do runtime reset, and that will delete your VM and give you a fresh one. So that's how you restore it. All right, anyway. We're importing TensorFlow, we're making a data set, and I'll explain what this is. So here's our data set, and I've created some random points that are like roughly linear. And this example isn't really good for teaching machine learning, but I'll explain what's missing. Another word for machine learning is prediction. So given some data, how can we use that to make predictions about future data? And basically, you always need two things. You need a training set and a testing set. And the training set is the data that you're given, and the testing set is the future data that you never get to see that you need to make solid predictions on. So you can imagine this like you're a doctor, and the training data is what you see in medical school, and the testing data is the first patient you have to diagnose when you get out of school. So it's very important that you get it right. And most of machine learning, people think about how many layers should I use in my neural network, but it's really thinking through these scenarios properly. Like 90% of machine learning is about building a clean data set and designing a really thoughtful experiment so you know that your results are useful. What you see is deep learning when you Google it online is you learn about like, oh, hey man, like here's a 5-minute YouTube video and I'm gonna put like 19 convolutional layers and it's gonna be awesome and we're gonna train it, it's 99% accurate. Like that's a joke. And how many layers you should use in your model is rarely the hard problem you actually have. We'll get to that. Here we only have training data because this is just a silly example. So what we're doing is we're plotting our training data. This is all matplotlib so far, no TensorFlow. Now we get to TensorFlow. And the first thing you need in machine learning is a model. And that can be a neural network, or it can be y equals mx plus b. Here, we're doing this from scratch. So we're making two variables for our slope, m, and our intercept, b. And a variable, just like a weight in a neural network, is something that you can wiggle around. The idea is we start with random guess, and we will wiggle them until we find a good solution. And when you learn about gradient descent and backpropagation, it can sound complicated. But the thing to remember is, with any of these things, they're just numbers. You can literally make them a little bit bigger or a little bit smaller. And you just have to figure out which way to wiggle them. And that's all these fancy algorithms ultimately do. So we have two TensorFlow variables. And you can think of TensorFlow a little bit like NumPy. TensorFlow 2 works in the same way. So you can do like np.matmul, you can do tf.matmul. And the syntax is similar. All right, the first thing we need to do is a way to make a prediction. So given an x, how do we predict the y for that x? And here, this is our model. So our prediction is we just compute y equals mx plus b. In TensorFlow 2, this just works the way you expect. Even though m and b are variables, it just works in regular Python, which is great. And this operation, just so you know, will work with a single number, or it will work with a list of numbers. So all these operations are vectorized, which means they work on list of numbers. The reason we have vectorized operations is it turns out that most of the math involved in neural networks is multiplying matrices. We like to do that on GPUs because they do it fast. And the other thing GPUs do is they can multiply many matrices in parallel. They have lots of matrix multipliers. So most deep learning libraries are written to work on batches or lists of data by default, which can be a little weird the first time you see it, but we just work with lists of stuff. And a trick you see, if you have just one example, often you have to stick it inside an empty list. So you have a list with just one thing inside it. And that's why that happens if you see it. The next thing we need after we make predictions is we need a loss function. And loss is a fancy word for error. So how bad were our predictions, basically? We need a single number that quantifies how bad of a job we did. In linear regression, we're going to use the squared error. So what we're going to do is we're going to look at all the y's we predicted, the y's we wanted, measure the distance between them, sum it up, square it, sum it up. That's our error. Lower numbers of error are better. If we have perfect predictions, which we won't have because our data set isn't perfectly linear, we'll have an error of 0. Anyway, here's how we do that in TensorFlow. We're squaring something we'll predict, the thing we should have predicted, and then taking the average of that. So that's our loss function. And this notebook is just showing you the initial loss when we start, which is some number that we want to reduce. So far, we haven't done any training yet, but we'll do that now. And the last ingredient we need is a way to reduce that loss. And we're going to do that via gradient descent, which is the reason I'm showing you this. This is exactly the same code we'll use to train a neural network, copy and pasted. Anyway, let me show you where we're going. So the notebook contains code to produce this diagram. And what we're doing is we're looking at loss as a function of m and b. And here you can see this was our initial guess for m and b. And that was a random guess whenever we ran this code. And what we're doing is, you can see that if we can find a way to take steps down to the bottom of the bowl, we'll have minimized our loss, which means we'll have found the best fit line. And the question is, so things to notice, first of all, this bowl has a minimum. Neural networks will not. And one of the reasons why deep learning was thought, or neural networks in general were thought not to work well, is because they didn't have a local minimum. So we can't find a perfect solution when we're trying to optimize a neural network. Turns out it doesn't matter. We don't need a perfect solution, but this was only obvious in retrospect. We just need a good solution. But here we can find a perfect solution. So the question is, how do we take a step down the bowl? And if you've taken a calculus class, you know you can use the gradient. The gradient is a vector that points in the direction of maximum ascent, and the negative gradient points in the direction of maximum descent. And you can compute that analytically. If you don't know calculus, which I'll assume you don't here, here's a simple procedure that will let us optimize our linear regression model. We take b, this is our first step. We increase b by a tiny amount. We compute the loss. We then decrease b by a tiny amount. We compute the loss. We figure out which way reduce the loss, and we wiggle b a little bit in that direction. We do the same thing for m. And we do that again and again and again. And this will be very slow, but it will work. The result will be the same, and we'll slowly be able to take steps down the hill. One thing you might start realizing is, if you wanted to do research here, you would say that, I know that my initial guess for m and b is going to be really bad, probably, because it's a random guess. So maybe I want to take a big step at first. And then after I've taken maybe 100 steps, I assume that my guess is pretty good. Maybe I'll take a smaller step, because I just want to refine it. So you might invent something called an adaptive learning rate. The learning rate refers to how large of a step you take. And here we're taking big ones maybe, and here we're taking smaller ones. And there's 50 million different ways to do this gradient descent. And a lot of them are built in. Anyway, so here's how we do this in TensorFlow. And this is the first time we do something actually useful. Gradient descent is an iterative process. So we're going to do this for some number of steps I pulled out of a hat. This is going to be our step size that I pulled it out of a hat. You're starting to see that we have all these magic numbers. You learn from experience which numbers are useful and which are not. All right, here's what we do. I'll come back to this gradient tape in a sec. The first thing we do is we make our predictions. So given our training data, we predict the y values for all the x's. We've seen how to do that. The next thing we do is we get our loss, and that's our squared error. So now we have this number. And now we finally use TensorFlow to do something useful. We say, TensorFlow, please give me the gradient of the loss with respect to m and b. And if you print that out, which you should, you'll see two numbers. And those two numbers together will be a vector that points up the hill. And what TensorFlow is doing, it's doing automatic differentiation. So it's doing the calculus for you to get that gradient. And what that literally tells you is if you wiggle these numbers in an infinitesimal amount in that direction, your loss will decrease. And all deep learning libraries do exactly this. So this is huge. And here, we're taking the gradient of something very simple, but the code works identically for something very complex, which is a neural network. Then what we're literally doing is we want to take a step downhill. So I'm taking the gradient, and I'm just subtracting it from m and b. And at the next iteration, our loss will be a little bit lower. And if we run this, and I ran the code above it, which I may not have, yeah, you'll see we have this iterative process where our loss goes down, which is great. We can print out the final values for m and b, and if you compare those to our the distribution we used to make the data, they're very similar, and then we can plot the best fit line. And so that's linear regression the slow way. But that's cool. So the last example we're going to use is Deep Dream, and the code is actually simpler than this. But I wanted to share this example with you because if you're new to gradient descent, it's useful. I need to see things. I need to see every piece. Like learning gradient descent with neural networks sucks because you have like 10,000 weights in a layer, and you print it out, and who knows what you're looking at. But here you can actually visualize it. So it's really cool. It's like a good learning tool. A good exercise you could do at home, which is not written here, if you wanted to understand gradient descent, you could pretend you didn't have this code. And what you could do is you could try and write a manual process to figure out the gradient for m and b. And that would be a really good exercise. And you'll get the same results. If it's right, it will just be very slow because we don't have time. There's different ways to calculate the gradient. It does it the fast way, which is reverse mode automatic differentiation, which sounds fancier than it is. All right. So let me show you some actual TensorFlow code. So I will basically talk until 7:15. Then I'll give you 15 minutes to work or take a break, and then we'll dive into cooler stuff. All right. So actual TensorFlow code. Let me just show you exactly how you can try this at home. So if you go to tensorflow.org, which is slow today, maybe they're updating it for the beta. Is that me or is that us? That's us. All right. So if you go to tensorflow.org, you should know that almost everything here is a trap, and you should ignore it, because most of the website is working with TensorFlow 1. I want to point you to the resources for TensorFlow 2. All of the resources for TensorFlow 2 are right now on tensorflow.org/alpha, which is where you should go. That may very soon change to tensorflow.org/beta, like tonight. And this is a disorganized resources collection of tutorials that we're building right now for TensorFlow 2. And what I want to do is walk you very slowly through the most basic tutorial that does deep learning to classify images. So if you want to try this at home, obviously there are advanced tutorials here in the advanced tutorials, if you want to poke around those now if you already happen to know this. But what I'm going to do is go into ML Basics and click on Classify Images. All right. All of the tutorials for TensorFlow.org are Jupyter Notebooks on GitHub. But just for convenience, I'm just going to run this in Colab. The way we make the website is we just convert the Jupyter Notebooks to HTML and stick them on the website. All right. So here's where we're going with this. Let me start yield boring install process. While that's going, let me introduce the data set. So for people who've taken a machine learning class, you've definitely seen MNIST. MNIST is a data set from Jan LeCun in the 90s. It was 60,000 pictures of handwritten digits that you might see in like a zip code on a letter, like 0, 1, 2 through 9. And there's 60,000 training digits, 10,000 testing digits. We often have large data sets in deep learning. MNIST became too easy. You would get like 99+% accuracy on it today in like 2 seconds. So there's a drop-in replacement for MNIST called Fashion MNIST, which is still very easy, but a little bit more interesting. Here we have 60,000 images of clothing. Each image is 28 by 28 pixels. So it's a little matrix of pixels. We've got a bunch of them. There's 10 different classes, like there's shirts, dresses, trousers, who knows what. And the goal is to train an image classifier. So given a picture, predict which class it is. And I will walk you through this and show you how easy it is to write a neural network to do exactly this. It's like, surprisingly, it's bizarre. This tutorial has lots of detail that you can read through. What we're doing here, which is not realistic, is this data set is built in. A lot of your own time is going to be spent collecting a data set. This is common. It's built in. We can import it. This data set is divided into train and test. And in both train and test, you have two things. You have your training images, and you have the label. And the label is what you should predict when you see that images. When you're doing your predictions on real data, you only get images. You never actually see the right result. You just have to make a prediction and deploy it. Here we have the right result because this is a game, and we're just going to evaluate how well we did. But when you actually deploy a model, this is what a lot of people don't realize. So here's a common mistake you make when you're learning about ML. Because you always have the training and testing data, what you do is, let's say you develop a model on the training data, and you try it on the testing data, and it's 90% accurate. Everyone wants higher accuracy, so you play with your model a little bit, and you try it again on the testing data. Now it's 92, and you play again, 95, 98, 99. And it's very easy to get a model that works super well in the test data, right? And so you feel really good about yourself. And then you deploy your model into production, and it sucks. And it's just horrible. And that's because you've done something called overfitting, meaning you've built a model that works extremely well on the data you have, but doesn't work well on data it hasn't seen before. And that's the goal. It's like a game that we play, and it's hard. So often, and the terminology here is weird, what we do is we need a way to simulate this process without actually cheating. We never actually want to look at this. So you'll often see a third data set. What you do is you take your training images and your training labels, and you randomly pull some of them out. And you call that a validation data set or an evaluation data set. And as you're developing your model, you can use that validation data set to see how well you're doing. That may or may not be shown here, but that's just FYI if you see it. We're in NumPy land. You can read this. The class names aren't included with the data set, so we're just writing like human readable class names just so we can see what we're predicting. A whole lot of deep learning is playing with the shapes of data. And it's a good skill to have. You can do this with, by the way, the name TensorFlow. A tensor in computer science land is an n-dimensional array. A number is a tensor, a list is a tensor, a matrix is a tensor, a cube is a tensor. If you're like an electrical engineering student, I know that there's way more to tensors than that. But in machine learning land, that's all we mean. It's an n-dimensional array. So that's tensor. Flow is a data flow graph. Behind the scenes, TensorFlow is a C++ data flow graph engine. And the reason we use data flow graphs is most computation can be represented as a graph. Anyway, that's where the name comes from. Basically here, this notebook is walking you through poking around with the data. And whenever I get a new data set, it doesn't matter if it's simple or hard, I spend a lot of time doing this. It's really important to understand exactly what you're looking at and get a feel for the data. And the reason is when your network doesn't work well, you need to have a hypothesis why. So you're never wasting your time by going really slow. We do things like plot it. You might want to pick random images and plot it. This can be less obvious than it seems. I can give you an example of that later. Here you'll see this a lot. What we're doing is the pixels as we've imported them happen to range between 0 and 255. And what we're doing here is we're normalizing them to be between 0 and 1. And we're doing that just for consistency, and for different reasons, neural networks work better when the input data is all in a small range. And basically, that's because we're going to be multiplying each of these numbers under the scenes now by a weight. And if the number is very large and we multiply it by a large weight, we can get things like overflow. So small numbers are better. What we're doing here, this is just more plotting code. This is more investigating the data. There's code here that lets you plot some images from the data set. None of this is TensorFlow. And here's when we actually do some deep learning. And let me show you why I was making those jokes about the YouTube videos. So let's say you've taken, this is going to be our model. So instead of y equals mx plus b, we're going to do a deep neural network. I'll explain the first part that's not machine learning, and then I'll show you how to do a deep neural network. There are many different types of layers in neural networks. The simplest type of layer is called a dense layer. And that's what you saw in TensorFlow Playground. A dense layer is fully connected. And what that means is that every neuron in the dense layer here is connected to every neuron in the layer before it, which in this case is the input data. So it's fully connected, so you have n squared weights. The way you write a layer like this in TensorFlow is you do layer.dense. There's other layers too that I'll try and get into called convolutional and recurrent and whatever, but dense layers are the most basic. Because dense layers take a list of numbers as input. Our images are 2D because they're pictures. What we need to do is unroll the images. So we're just going to take all the pixels, we're going to unstack it row by row, line them up into a long list. So this is just a layer. It's called a layer, but there's no machine learning here. It just unrolls the image. So now we have a single list of numbers. If we wrote our model like this, I need a diagram for this. I don't have it on these slides. What this happens to be, this is a list of 784 numbers, because that's 28 times 28. Each of those numbers is connected to one of these output neurons. There's 10 output neurons. There's 10 because there's 10 classes we want to predict. There are 7,840 weights in this model, because there's this number of inputs times this number of outputs. So in linear regression, we had 2 weights, or 2 parameters, and now we have 7,000. We're going to find good values for all those 7,000 in exactly the same way. If we wrote this code, this will work as is. This would be a model called multi-class logistic regression. Basically, we're training 10 linear classifiers, and you would learn about this in a machine learning class. If we wanted to make this a neural network, we would add this layer. Now we have a neural network. If we wanted to have a deep neural network, we would add this layer. Now we have a deep neural network. If we wanted a deeper neural network, now we have an extremely deep neural network, and you've just watched your 5-minute YouTube video, and hey man, here's how you do machine learning, bro. It's going to be super cool. So now we have a deep neural network. Deep neural networks have 2 things. they have depth, and here the depth is the number of layers, and they have width. And the width is this parameter here. That's how many neurons per layer. And roughly, you can think of this as a pattern recognizer, and no one has intuition for this at all. The depth of the network is the number of combinations of patterns it can learn. And we can actually see this directly. I'll try and get to it. The basic idea is that the first layer is looking at pixels. If you have features of pixels, combinations of pixels will give you edges or lines. Maybe this guy recognizes lines. This means roughly there's 128 lines that it can detect. Combinations of lines give you edges. Combinations of edges give you shapes, textures. And if you have a very deep neural network, layer 20 might end up learning how to recognize eyes. And we can actually show you this. It's really, really cool. The representation learning in deep learning means that these layers automatically learn to recognize useful features in the image. This network would be way too big. Why don't we use enormous networks? They take a long time to train, and they overfit the data. A deep neural network will just memorize your data set, but it will do badly on the test data. So here, I'll just run this a couple times so you can see it. We'll start with our linear classifier, and we can define the model. By the way, in TensorFlow 2, there's different styles of defining your neural networks. The most common style is sequential, and 90% of networks from beginner to advanced fit into exactly this. A sequential model is literally a stack of layers. You can also have a graph of layers, but a stack works for almost everything. In the beginner style, we're going to compile this model, and this is easier than the linear regression. I mentioned that there's a box of gradient descent algorithms. If we did SGD, that's the most basic one, and that's exactly what we did in linear regression. There's a paper, Adam, and Adam proposed a gradient descent optimizer with adaptive learning rates and per parameter adjustments and all this fancy stuff. But we can just, because it's so common, we'll just use Adam. Obviously, if you were using this for medicine or something really important or to control a rocket, or if you really wanted to debug your model and make sure that it worked well, you need to gradually learn more details about these. But we're just going to black box Adam, and it's great. This looks scarier than it needs to. Our loss function for linear regression was squared error. Here, our loss function here is called, let's just say cross entropy. Cross entropy is a loss function used in classification problems. And I don't have a slide for this handy, but the basic idea is we have an article of clothing, and it could be one of 10 things. And we're going to predict a probability distribution that says how confident we are that it's each of those things. So it's 10 numbers. Each number is between 0 and 1, and they sum up to 1. So let's say we're really confident it's a boot. We'll put 95% of our confidence on boot, and we'll distribute the 5% randomly through the rest of the digits. We need to quantify how bad of a job we did. So let's say it's actually a boot. So the label is going to have a 1 on the boot and a 0 on everything else. And the label's 100% confident it's a boot, because that's the right answer. Cross entropy lines up these distributions, and it compares them. And the farther apart these distributions are, the higher your error. So cross entropy is a loss function for classification. And the rest of the stuff we're seeing is implementation details, which looks scary, but there's a very limited number of options. And you learn them as you go. In linear regression, we did the gradient descent steps manually. But here we're going to use a built-in method. And what we're saying here is TensorFlow, please train my model. It's called fit. It's a word from statistics. Please train my model using the training images and the training labels. And a really key question you have to come up in deep learning is how long do you train it for, which is epochs. An epoch is a sweep over the data set, using every training example once. The longer you train your model, the more accurate it will be. So if we train this for a bazillion epochs, here's how you get 100% accuracy on the training set. You make a very deep neural network with very wide layers, and you train it for a large number of epochs. And the accuracy should eventually go to 100. The reason we don't do this is we don't care how accurate it is on the training data. What we need is a model that's accurate on the testing data. And so here we'll just train it for some epochs. As we train it, I'm not sure if I enabled the GPU here or not, but you can see the starting accuracy is low, and over time it should hopefully increase. And it's not going to be super high because my model is very simple. We're using a logistic regression model. When it's done, we have our trained model. And here's how there's a couple things you would commonly do. I'm going to start moving a little faster. You might want to evaluate our accuracy. Here we're cheating. We don't have a validation set. Never do this, but who cares here? So we're just evaluating it on the test data. And we've built a model that's 70% accurate. And that's actually not so bad because there's 10 different things. So our baseline would be 10% if we were making random guesses. That's not terrible. And now let me show you how we can do the modeling process where we make a more accurate model. Actually, I'll let you do that. So I will stop talking for 5 minutes if you have a laptop. And a very simple exercise would be increase the accuracy of this notebook. And here are the two parameters you get to adjust. Here we trained a very simple model for 5 epochs. So one thing you could do is increase the number of epochs. Make that 10, might be more accurate. Another thing you can do is convert this to a neural network. I mean, I deleted the line, but you could get the line back so you have a hidden layer, and then you could actually make it a deep neural network. So here's, oh God, here's a neural network. Here's a DNN, and other parameters you can adjust. These don't have to be multiples of 2. We just do it because we like multiples of 2. Those will affect the accuracy too. And what you're doing right here, this is called modeling. And this is the smallest part of the entire machine learning picture. But it's what gets a lot of attention because for whatever reason, this is viewed as cool. So I'll start again in 5 minutes. And does anyone have any questions? I know I've been talking a lot. Thanks for listening. Yeah.
Just more on your own opinion or professional opinion. How effective is dropout to avoiding overfitting?
I'll come back to dropout. The question was how effective is dropout to avoiding overfitting? We probably won't cover that today. Very. And the other nice thing about dropout is it's very simple. Because your other option is let's put regularization on the layers, and then it's like how should you regularize it, and then there's math, and dropout works well. So it's great. Yes, I'll just go around the room this way.
Just to thank you for the developers, it's working great on my iPad.
Awesome. So the comment was it's working on an iPad. Yes, I didn't develop Colab at all, but the team is phenomenally good, and you can literally run it on your phone. So if you want to work all the time now, you can. The important thing about Colab for students is it means nobody needs to buy a GPU because it has one built in. Here we don't need it, but you do need it for the fancier examples. Yeah?
So you made a statement that when we increase the depth of the network and train more, we're going to reach better or less error.
Yes.
And I agree with you. I see that. Is that an intuition we have, or is there a mathematical proof that it is always going to be true?
Oh, really great question. Is there a mathematical proof that if you increase the depth or the capacity of the network, that the accuracy will always be higher? I don't know. I'm not a theoretician. We would have to sit down on archive and start reading. Intuitively, what we're doing is we're increasing the capacity of the network. By adding more parameters, we're giving it more degrees of freedom to fit the data. Another way intuitively is, at a certain point, you might get diminishing returns. It may be that after you have 12 layers, one of them is able to very accurately model what a boot looks like. And more layers just mean that it takes longer to train. A lot of deep learning is empirical. Thank you very much, which is a blessing and a curse. I'll start again in like 3 minutes. By the way, is this too fast, too slow? You don't have to say, like, too fast? Oh, thank you. Awesome. Cup holders. Too slow? All right, I will go maybe just right. I will go a little bit faster in the second half. And the goal is not to understand everything, but it's basically to get some of the key ideas and then get links that you can try at home. And every cool idea I'm going to show you, which seems kind of researchy and magical, has a no BS. Here's a link to the complete code that does exactly what I show you. Yeah?
You said the first layer is basically logistic regression. In the context of stats, there's a concept of inference, right? Is there a concept of inference as you go down a layer?
Is there a concept of inference? Yeah. So a lot of the words in this, by the way, I realize to statisticians a lot of what I'm saying is kind of hand-wavy, in the same way that when I talked about tensors, that seems hand-wavy to an electrical engineer. What machine learning and deep learning have done, we've taken concepts that have existed for a long time, like linear regression, logistic regression, and we've basically rebranded them. We're like, no, that's a machine learning thing, so we can get paid more money to do something that everyone else knows how to do. Inference we're doing all the time. Here, the word we're using for inference is predict, and you can also think, if you took the output of one of those intermediate logistic regression units, you can treat each one as, I'm not sure if you would technically call it inference, but it's part of the forward pass of the model. I don't think it would correctly be called inference because we're not actually using it to classify the data. What we're really using it is to produce a feature that's useful to subsequent layers. And what those neurons ultimately train to do is just that. And we can visualize those features if we go a lot faster, which we will.
But there's not a concept of p-value or something like that?
No, there's no concept of p-values here at all.
Okay.
I didn't talk about it. The output layer of the neural network, to get into p-values, has a softmax activation. And didn't have time to go into this, but softmax squashes the output into a probability distribution. It's not a true probability distribution, it's a confidence score. But we call it a probability distribution because it ranges between 0 and 1 and sums to 1. But I wouldn't go to Vegas and bet proportionate or in exact probabilities corresponding to the output of that. I would treat it as a very rough confidence score. Yeah. Yeah?
With regards to the example, I guess what's the target accuracy that you think would be good?
You'd have to check papers. Off the top of my head, I'm not sure what the target accuracy is for fashion MNIST. I want to say like mid-90s, give or take, with a dense network, maybe higher with convolution, I'm not sure. It's not great. There might be a way to get 99, but I haven't played this example too much.
Just wanted to ask about the width of the nodes that you had put in, 128, 256, any sort of a rule of thumb, a practical
Are there, great question, are there rules of thumb? Not really, and the rules of thumb are if you're doing this in practice, from experience, so I happen to know that this works reasonably well, there are lots of standard architectures. By an architecture, that's what we're looking at right here. There are standard designs or architectures for models that we know work well for different problems, and we reuse them all the time. So if I was working with actual pictures, I might use an architecture called Inception. And Inception is built into TensorFlow. It's also a paper. It's just a very deep neural network and a particular arrangement. And if you search for like Inception, whoops, not the movie, V3, here's a picture of what the network looks like. And basically, there's different types of layers in here, and it's a complicated diagram. But basically, TLDR, you're looking at a very deep network with some fancy features. So our little MNIST network had, I forget, 4 or 5 layers, and here we might have 20-ish. And there's other things too. But we can import this and reuse it out of the box so we don't have to rewrite it from scratch every time. Yeah?
Oh, thank you. Are there common resources for those pre-cooked architectures? And
Oh, yeah.
Oh.
Great
okay,
question. Are there common resources for the pre-cooked architectures?
Yeah.
Yes, definitely. So I will show you that when we get to the Deep Dream notebook, which I might just do next, just for fun. Yeah.
Cool.
Can we get the link for the slides again?
Oh, yeah, bit.ly/ICSE3. Hold on, let me just get my place. That guy. All right, I'm going to talk for 2 minutes, then we'll take a 10-minute break, and then we will keep going. So basically, just to move a little faster, what we've seen is this style. There's different ways to define your networks. Here we've used the beginner style, which isn't really beginners. This works for research too. We're bad at naming things. But this is exactly what you just saw. This is a complete neural network in TensorFlow 2. It's called beginners because we're using the sequential API. So we define our model as a stack of layers. Great. There's another style we can use too. And it's this. So this is new in TensorFlow 2. It existed before in Chainer and PyTorch, and I believe Gluon. And what we're looking at here is, this is object-oriented NumPy programming. What we're doing is, in all those libraries I mentioned will provide a class, and they call it something differently. Here, TensorFlow is called model, and Chainer, I think it's called network. Basically, the library gives you a class. The way you implement your neural network is by extending the class. So here we're extending the class. We made my model. In the constructor, if you're from Java, this would be great. You define your layers in the constructor. And then the forward pass of this model, or the predict method, here is called call. And you write the forward pass imperatively. So here we're taking some input data, that could be an image, we're passing it through the dense layer, we're getting the result, we're passing that through another dense layer, and we're returning the result. And this is perfect if you want to do, actually if you're a student, this is great too. Because maybe you're curious, you want to know exactly what the inputs look like. Because this is regular Python, as you would expect, you can just do print inputs. If you want to see exactly the output of the dense layer, you would just print X here. If you wanted to write your own layer, it's trivial, it's just Python. So this is great. The reason that there's a huge con to this too. So the pros are this is like super hackable. There's a huge con, which is not obvious, and this is a software engineering thing. So when I'm debugging a student's code, if she writes it like this, there's a correct way to use this style of code. It's a stack of layers. Because this is defined in a consistent way, what you might not realize is when you call model.compile, TensorFlow can help you debug. We're catching errors at compile time before we start pushing data through the model, which is great. This means that the bugs that are going to exist in your model are going to be conceptual bugs. meaning your layer was too small or you didn't use the right combinations of layers, but they're not programming bugs, which is huge. In this style, here, what your model is under the hood, there's a data structure, and it's a stack. We understand stacks very well. In this style, your model is a piece of Python bytecode, which means you can do whatever you want, which is great. There's also nothing we can do to help you out. So you get, in this style of code, you get programming errors at runtime, and you get machine learning errors at runtime. And there's also fewer standards for this. So maintainability is a huge issue too, right? Just like in software, you write software once, and it's run and edited like 10 times. It's the same thing with machine learning models. And so if your friend Mike at your company writes his model in his funky style, you have to learn Mike's style to debug his code, which is horrible. But anyway, it's great, because it's fun to use, but there's a cost. Anyway, so I'll stop talking there, and I'll start again at 7:30, 8 minutes. By the way, both of these models can be trained with model.fit or gradient tapes. All right.
So there's still soda left. If you want water,
So on
there
the
are
status
cups,
station,
and
I'm
there's
sort of
a
like
drinking
that guy.
fountain
Awesome.
near the restrooms.
Only know machine learning from theory. New
That's all right. Whoops. I've had a lot of coffee. Oh. All right, we'll start again in just 30 seconds. All right, so now we can do some more advanced and fun stuff. So I mentioned that deep learning runs in JavaScript too, and this is a program you can try right now if you want. It's bit.ly/pose-net, and I'll just show you. So this is deep learning running in JavaScript. It's written in TensorFlow, but it's using something called TensorFlow JS, and it's running entirely client-side. So no data is being sent to a server. Don't worry, I just probably popped the plug. Come back, plug. All right, give me just one sec. Ah. Any longer.
You know, if worse comes to worse, maybe just borrow somebody's laptop.
Yeah, that's a good idea, home. Oh, it could have been that. Thank you, you rock. Thanks. Yeah. All right, I'm gonna try this one more time and hopefully it won't break it. Carefully, carefully, carefully. All right, let's see. Yeah, it's cool, right? So this is PoseNet. It's running entirely locally. None of this data is being saved or sent anywhere, so this is great. And so it's not meant for this many people. But what's really cool about running machine learning in JavaScript, which was non-obvious to me, right? So I'm a Python developer. So I'm like, when I heard about JavaScript, I'm like, that seems silly, right? Because we already know that Python's a little bit slow, which is why we have this C++ backend. And JavaScript's even slower, right? So I was like, that's silly. Why are we going to do this? I'll fix it again. But the answer is obvious if you're a JavaScript developer. And it should be obvious now. So if you write it in JavaScript, it can run in a browser, right? As it happens, browsers also run on phones. So now you also have a mobile app. And it can be fast because the computation's not fast, although now it's actually pretty quick. But you don't have to upload images to a server every time, which also means it can be private. And so machine learning in JavaScript is huge. And the reason I'm sharing you this is if you're a JavaScript developer, TensorFlow JS is really good, and you actually never need to go to Python. What you can also do with TensorFlow JS is convert a model that you've trained in Python and run it in the browser, which is what happened here. So there's all sorts of possibilities. Another possibility here is even if you're not a machine learning developer and you just want to reuse an existing model, there's all sorts of stuff you could use this for, games or whatever you can think of. Like to pull a humanitarian application out of a hat, it can do eye tracking too. So like a no-brainer application is if you have a quadriplegic, you can watch his or her eyes, and you can use that to track a mouse cursor. And presumably there's like a million more cool things we can do that are, anyway, it's like a whole new thing. So let's do something more advanced. And I will arbitrarily choose Deep Dream, which I have a crappy slide for because I made this at the last second. But here's code you can use, and then I'll explain what Deep Dream is. So the code for this is bit.ly/mini-dream. So it's mini dream with the dash. And let me show you what Deep Dream is, and then we'll talk about what it is, and then why it is, and how it works. So if I search for Deep Dream, right, we get all sorts of crazy psychedelic images like this. Let's take the Mona Lisa. So Deep Dream is a software program now in TensorFlow. Originally it was in a cafe, I think, from 2015. And Deep Dream made pictures like this. And so what do you see when you look at the Deep Dreamified Mona Lisa? Like what stands out? Dogs, yeah, there's dogs everywhere, or bits of dogs. So I see, there's no right answer here, but when I look at this, I see dog snouts and maybe eyes.
Snakes.
Snakes, yes, good eyes. There's definitely snakes. Fish, for sure.
Peacocks?
Peacocks. So why are we seeing all these things? I hadn't seen the snakes before, so I'm glad you saw that, because I was going to show snakes later. Oh, yeah, holy crap. Anyway, scales.
Multicolored scales.
Yeah, so this is super psychedelic. Now, does anyone know why does anyone randomly read the Deep Dream paper? So Deep Dream was an experiment, and it happened to produce images like this. The goal of Deep Dream was not to produce psychedelic art. This is a happy accident. The goal of Deep Dream was to investigate. So if you train a neural network, specifically a convolutional network on a large data set, it can classify images like cats and dogs with high accuracy. The question is, why is the network so accurate at classifying images? How does the network work? What's it doing? And I've been really hand-wavy about like, oh, we have like this layer that recognizes textures. But Deep Dream is a way to see exactly what the layer has learned to recognize, and we can actually visualize it. And I'll show you the reason that we're seeing, what we're doing in Deep Dream is we take an image of the Mona Lisa, and we choose some layers from a neural network. And here, I don't know exactly the names or the numbers of layers that they've chosen, but you choose some combination of layers. And then what you do is you modify the image to increasingly excite those layers. So the hypothesis would be that if you have a neuron in a layer that detects edges, and you forward the image through the network, so you classify it, you record the output of that layer, and then you find a way to modify the image to make that output stronger. And if there's a layer that recognizes eyes, and you do this, then you'll see eyes in the image. And let me show you a little bit more concretely how this works. I should probably go to my link. So this is the minimum amount of code you need for Deep Dream. The paper that produces these really high-res, pretty images has like a whole bag of tips and tricks, which I just skipped. But I just wanted to get you the minimum code that does the thing. And what we're going to do is, while this is installing, is we're going to take an image like this, and we're going to produce an image like this, using code that looks almost identical to linear regression, surprisingly. So while TensorFlow 2 is installing, let me just, I'll go fast here. But basically, the first like 40% of this notebook is me being a bad Python programmer, and here I'm just downloading an image from a website, normalizing the pixels, and loading it into memory. And I wrote it this way just so you can see exactly like how it's being normalized and what all the steps are. So at this point, we've just pulled some picture into RAM. Earlier, we talked about pre-trained neural networks. And I mentioned Inception v3. Here we're importing Inception v3, and that's that monster neural network you saw earlier. And this is a pre-trained network. And it's been pre-trained from a data set from Stanford called ImageNet. And ImageNet has 1 million different pictures and like 1,000 different classes. Cats, dogs, snakes, flowers, peacocks. All those trippy things that you saw appear in the Mona Lisa are images that exist in this data set. And this is a generic classifier. ImageNet is really popular because it's a standard data set, and it's used for, just for research to compare different models. But if I had a picture of like a cat on my laptop or whatever, and I just did Inception v3.predict cat, that would probably say cat. So right now, this is just a complete TensorFlow model. And this is the first ingredient for Deep Dream. What's interesting, though, is we don't want to use this model for inference. I don't care about predicting cats. What I want to do is pass an image through the model, and my goal here, let me see if I still have that picture of Inception v3, or any picture. If I classify my cat, what I'm really doing is I'm looking at the cat goes in here, goes through all the layers, and out of here comes a probability distribution. Inception, as it's trained on ImageNet, knows 1,000 different classes. So this is a list of 1,000 numbers that range between 0 and 1 and some to 1. I don't care about that, though. What I care about in Deep Dream is, let's say I want to get the output of this layer. And specifically, maybe some neuron in this layer. Whoops. And when I start this experiment, I have no idea what some neuron in this layer has learned to detect. But my goal is to find that out. Great question. And here's, how do you choose which layer? And the answer is experimentally. Great question. You choose it experimentally. And I'll show you the mechanics. When the authors wrote this model, they conveniently named all the layers. And when you write a TensorFlow model, you can have another parameter like name Josh's favorite layer. But here they have different names. And I know these, what I'm doing here is I'm writing a model to get the output of these layers. And I'm choosing these layers because I saw in a different implementation that they worked well. You can try other ones. And if you want to see all the layers in the model, you can do something like this, Inception v3.summary. And that will just print out all the layers. I'm writing a new model here, and this is a different style of TensorFlow, which I don't want to go into details. It's called the functional style. You could write this using the subclassing style too. But what I'm doing here is for each layer, I'm asking the model to get that layer, and then I want the output. And I'm writing a new model And the idea here is I'm passing it some image, and instead of getting the output of inception, what I'm doing is I'm getting the outputs of all that, of the list of layers that I just specified. So this will give me a list of numbers, which is the activations coming out of those layers when I classify an image. Yeah?
With like the new TF eager stuff, how do you do this?
Great question. So how do you do this with TF eager? So for eager is an interesting word. Eager just means normal imperative Python. TensorFlow 2 is eager by default. And the reason I didn't have to mention it is because it just is. So this is doing it with TensorFlow eager. Here, technically, I'm using a style called the functional style, which is symbolic. You could rewrite this using model subclassing if you wanted to.
Right, so like to get the outputs of like a specific layer, normally you can just do like session.wrap.
There are no more sessions.
Right.
To get the outputs of a specific layer, you would do exactly this. You would just do print x.
But so you have to have like currently you can like reach into the network and pick out an output.
The reason we're reaching into the network, great question. The reason we're reaching into the network using the functional API is this network was defined using Keras layers. And because it was defined, I'm pretty sure it was built using the functional API, we have these really nice layer names and it's easy to pull out specific layers. If it wasn't written in this way, what we would have is some class. These aren't my speaker notes, I stole this slide from somebody. The class would read inception B3 or whatever. And this would be huge. And this would be pretty big too. But we'd have the actual bytecode, and so we could just modify this, or you could write a new function. You could do def, ax, and then input image, and then you would do something like return my layer, well whatever. You just write the forward pass in there. So basically, yeah, those are your options. This is a good thing. So TensorFlow is a big framework, and it has lots of different ways to do things. But it also has a large learning curve because of this. But in 2, at least they're all really sensible. I'll show you a trick with the graph mode in a second. I don't know why I wrote it this way, but anyway, this is 30% of Deep Dream. We have an existing model. It's been trained on a large data set. We're forwarding an image through it, and we have code that will give us the activations of some layer. Great. So that's 30%. And in the forward pass, I mentioned early in the talk how networks usually works on lists of images. They take a batch of images as input. Here I just have a single image. And whenever you see code like this, you'll see this all over the place. It can be written in NumPy expand dimensions or TF expand dimensions. What this means is we're just taking our image and we're sticking it inside an empty list. And this is just so we can forward it through the model. It's an implementation detail, because this is just the shape of the data that the model wants. And if you want to understand exactly what this does, a really good thing to do is just, do print like image batch.shape, and you'll see exactly what you're looking at. All right. The second ingredient in deep learning is a loss function. And here, and this is where we get into research, our loss function is how excited these layers were by the image. So what we do is we have all the activations, and we're just going to sum them up. And there's some normalizing code here, because I found it in the paper and copied it. But what we're really doing is we're just saying for each layer that we picked, and that's going to be the layer called mix2, mix3, mix4, whatever, the activations is a list of numbers, and that's the output of all the neurons in that layer, and we're just summing it up. So our loss is a single number that says how excited or how activated were these layers are by our image. And then we have the last piece of Deep Dream. And this is really cool. You might recognize this code from linear regression. But there's one trick to Deep Dream, which is this. Almost always in a machine learning model, you adjust the parameters of the model. You don't change the data. So if your fashion MNIST classifier is not very accurate, you wouldn't be like, oh, no problem. Let me just draw on the images until it gets them right. Right? But that's what we're going to do here. So in Deep Dream, the model never changes. And our model is inception. We don't adjust it. But here's the secret to Deep Dream. We take our input image, and we treat it as a variable. And let me show you what you can do once you have that. Here's our training loop. We take the image, we forward it through inception, we get the activations of the layers. We get our loss, which is the sum of those activations. And the magic of Deep Dream is this. So we say, TensorFlow, please give me the gradients of the loss with respect to every pixel on the image. And this will return a list of numbers that tells you for each pixel, if you wiggle it up or down a little bit, increase or decrease the intensity, how that will affect your loss, or how that will increasingly excite the layer. And then what we can do, this is from the paper, I'm just normalizing that, we can literally add those gradients directly to the image. So now we're modifying the input image. And if you repeat this a couple hundred times, and you can actually display the image as you go if you want, you'll see these like psychedelic faces start to appear in the image. And that's because the layers that we've chosen are responding very strongly to those features. And this is actually a really big deal, even though like this isn't very high resolution. The fact that we can do this proves that deep learning is representation learning. And what we've gotten for free is inside that network, there's some neuron, or some layer in this case, that gets excited by things that look like that. And if we start, a follow-up to this is instead of making a psychedelic image, we can start from an image that's random noise. And we can try and generate an image that maximally excites a layer starting from scratch. So we can ballpark understand what these layers recognize. And linked at the bottom here, there's a link to the paper, or an implementation that was done by a researcher. Yeah, this is the Deep Dream author, or one of them. And this person has directories of different images that really excited different filters in each of the layers. And so the first layer is looking at pixels, so simple colors, simple edges. And these are images that made different neurons in that layer very excited. And they're simple. The takeaway here is simple shapes, simple colors. As we go deeper into the network, so now we're looking at, this layer is looking at combinations of combinations of combinations. And there's neurons that are responding really strongly to these things. And some are quite beautiful, right? This is really cool. And the takeaway here is none of these were manually engineered. These were all found incidentally, or along the way to training an image classifier. The network did this as an artifact of the job we gave it to do, which is super, super cool. And as you go deeper into the network, the patterns get more abstract. And here's things that you're starting to see that look deep dreamy, right? The reason that we're seeing shapes like this is ImageNet from Stanford happens to have tons of peacocks for whatever reason. So this network responds really strongly to peacocks. It also has snakes. And if you scroll through this long enough, don't do this when you're not sober, you'll find some really, really interesting things in Deep Dream. Anyway, you can spend a lot of time on this. And then if you go really high level, you start to see things that look a little bit like you can almost start recognizing maybe these are ants, right? Right, so now we're starting to see, maybe this is from a chimp, we're starting to see like faces, right? And so, but this is called representation learning. And deep learning is representation learning, right, which is a big deal. So anyway, the TLDR of this is the code is in that little notebook. There's the paper at the end of it. Let me show you some other cool things you can do with deep learning that are non-obvious.
So if a neuron is excited by this image, is it rarely excited by a different kind, or?
Great question. If a neuron's excited by one image, is it excited by others? And the answer is usually it's excited by many different combinations, just to different degrees. I really want to, okay, hold on, I need to stop presenting for just one sec. I'll plug this right back in. I'm going to go into my drive, and I just want to, we don't have time to do convolution, but I want to pull up some slides and explain exactly what those layers are, because they're not dense layers, they're convolutional layers. All right. I'm just going to guesstimate for one sec. Yeah. Right. So these are layers that are convolutional layers. And you can write a convolutional layer in TensorFlow by saying, instead of layers.dense, you'd say layers.convolution2D, or conv2D. And convolution is not a machine learning concept, but I want to explain briefly what convolution is and why this works. So convolution, this is from a library called SciPy. And the goal of this slide was just to show you that you can do convolution without TensorFlow. And here's a question, by the way. So when I wanted to teach convolution, I wanted to get a picture. So I imported the built-in picture from SciPy. And it had an astronaut, and I thought that was super cool. So I imported the astronaut. And does anyone know who this is? She's famous enough to get built into SciPy. Very good, close. Sally Ride is a great guess.
Sally Ride has black hair.
Ah! I didn't know that, but I do now.
I think it's my ex-wife.
You missed out. This is Aline Collins, and so she was the first woman to command the Space Shuttle Columbia, which is a really big deal. So now she's built into SciPy. Anyway, we're doing edge detection on Aline Collins, and we're doing that using convolution. And convolutional networks, so a dense layer, I mentioned it was fully connected. It has tons of weights. It's n squared weights. It's the number of input neurons times the number of neurons in the dense layer. So they're super inefficient. Convolutional layers have a very small number of weights. This particular layer would have 9 weights. It's this little, we call it a kernel or a filter. And this kernel can do edge detection with just 9 weights. So the way we find all the edges in the image, if we convolve that, we'll get an output picture that looks like this with the edges in the image. And I just want to show you what convolution means. What convolution means is we slide the filter across the image. We take the dot product of the filter and the pixels under the image. And that literally just means multiply -1 by whatever pixel intensity is beneath it, plus -1, plus all that. The reason this gives us an edge is there's 9 values in this filter, one of which is 8, and the rest are -1. So if all the pixels beneath the filter are the same color, or the same intensity, the filter returns 0, because there's no edge. If they have a big difference, it returns a large number. So this is a very simple edge detector. Here's how it works. Basically, this is convolution, at least in the machine learning sense. Again, if you're an electrical engineer, I know there's a lot more to this, but this is machine learning convolution. We have an image and a filter, and we slide the filter across the image, taking the dot product as we go, and out comes an output image. What's really important is the takeaway is that with a small filter, it can do really sophisticated things. And this is an edge detector that I wrote manually. If you use Photoshop, that uses convolution to do sharpen, blur, all that stuff. And those are really nice filters written manually by engineers who put a lot of thought into it. Anyway, the convolutional layers have these filters too. And what we're seeing in Deep Dream is we're creating images that excited some filter. So what we're seeing in Deep Dream is really there's some layer that has a filter that responds to something like that. And that's also one reason why we see lots of repeating patterns. You see how these patterns are repeating again and again and again. And that's because these filters are literally sliding across these images. But anyway, these are convolutional layers, and they work very well for image classification. All right, other cool things. Here's another crappy slide that I made at the last second. Oh God. This I don't have much to say about, except I just wanted to give you a link. Let me see if I can make this less crappy so you can actually see it. So this is a minimal example of doing image colorization with deep learning. And as you might guess, it's bit.ly mini-color. This is the world's simplest, but also worst example of image colorization. Worst in the sense that the training set is one picture. And the reason is it just memorizes it. This won't generalize at all. But this is the minimum amount of code that you need to do the thing. And it will also run in 2 minutes. So you can just train it very fast. The goal, obviously, is you take a black and white picture and you color it in. And the one thing I wanted to share is not the machine learning chunk, but it's actually about how you represent images. And normally when we think of images, we have 3 color channels. We have red, green, and blue, right? So an image, it's not a matrix, but it's actually a cube. And we have the red pixels, the red intensity, the green intensity, the blue intensity. But there's a trick to this. And what we do is we represent the image in lab space, LAB. So we convert an RGB image to an LAB image. And there's still 3 color channels. But the first one basically represents the lightness or the grayscale version of the image. The next 2 color channels represent the color. So a common question when people learn about colorization is, are we predicting this entire image from this one? And the answer is no, we're just predicting the color channels. So this is a problem called regression. And for each pixel, regression means predict a number. We're predicting the number that corresponds to the color intensity of that pixel in the output image. So we literally copy the grayscale image to the output, and then we color it in. We don't generate an image from scratch. And oh, bit.ly/mini-color. It's not that? That's sad. Hold on. Let me see if I messed this up in my haste. Nice. That. All right, well, I mean, that's great too, I guess. So let's make a new link. That's actually really sad. So what that tells me is that either bit.ly just screwed this up somehow, or no one's actually tried this at the last talk that I gave. So let me just fix this really quick. You can see the magic and excitement of creating bit.ly links. All right, so it's minicolor 2. And minicolor 2 will get you to GitHub. But let me show you the trick to get from GitHub into Colab. Mini-color 2. One way is you can download the notebook and upload it to Colab with the UI. Another thing you can do, there's a browser extension you can get. If you search, I think it's probably called the Opening Google Colab browser extension. And it gives you this little button. You can click the button and it just opens it up, which is really sweet. Or here's how you change the URL. You delete the .com and you write colab.research.google.com/. And then it will just open it up from GitHub, which is great too. This is all notebooks. This is helpful. Anything on GitHub. This is really helpful too because the GitHub built-in viewer is awesome, but it doesn't always work for enormous notebooks. I don't have time to go into this in depth, but I just want to say that a surprising thing about deep learning is this is the complete model. And it's using these convolutional layers that I mentioned earlier. And that's it. And this is all you need to do image colorization. And this type of model is trained in exactly the same way as you would see other ones. So that's the takeaway here. I'm going to keep moving, but you can play with that. Let's talk about GANs, I guess. Now I'm going like super, super fast. The takeaway here is not to try to understand these models, but it's to have like links. So if you're curious, you can. What we always have is complete code. So you can go through it and play with how it works. Really to understand, I'll talk about GANs, which are an amazing idea. To really understand GANs would take a few months and time. But let's just give the basic idea. So GANs are called generative adversarial networks. And a lot of the examples, aside from Deep Dream that we've talked about, are about classification or regression. And that's the bread and butter in deep learning. The number one most common skill is I have some data, I need to make a prediction. Great. Or, right. Generating data is much harder. So it's relatively easy. If I give you a picture, you can say, this is a cat. Much harder if I ask you, generate me a picture of a cat. And that's way harder. And that's what generative models address. And GANs are a deep learning solution to generating data. And it can be of any form. It can be an image, it can be a sound, whatever. And here's how it works. In deep learning, one of the ingredients is a loss function. We have to have a number that says how bad of a job our model does so we can adjust the parameters to make it do a better job. The question is, for a generative model, how can you get a number that describes how fake your image is? And the solution that the author of GANs came up with in 2014 was that we already have it. We have neural networks that can classify images. So these were invented by a PhD student at the time, who's now super famous, Ian Goodfellow. And does anyone know what Ian was doing when he came up with the idea for GANs? He was drinking. The reason I'm mentioning this is you should take a break from your research sometimes. So here's the basic idea. There's two networks, and we train them simultaneously. We have a generator, and the generator is responsible for generating images. And that's new. And then we have a second network, and that's a discriminator. And the discriminator is just an image classifier. And that's something that we already know how to build. And it literally, if we were doing cats, the discriminator would be trained on pictures of cats. And the prediction task is real or fake cat. What's interesting is the generator never actually sees a picture of a cat, ever. All the generator sees, it starts by generating an image, which is going to start life as random noise. All it sees is, did the discriminator determine if that was a real or fake cat? If the discriminator says it was a fake cat, we use the gradient trick in the same way we did the gradient with Deep Dream. We get the gradient of the discriminator's loss with respect to the generator's variables. And that tells us how to adjust the variables in the generator very slightly to fool the discriminator slightly more at the next iteration. So the next time the generator generates an image, it looks slightly more cat-like, but the discriminator still says it's fake. But if we train these models in parallel for a very long time, eventually they stabilize, and we get to the point where the discriminator can no longer say if a generated cat is real or fake. And then at that point, we have an image generator. We use MNIST a lot in deep learning, and when you start with, this is the original MNIST, not fashion MNIST, was data sets of handwritten digits. This is an example of a GAN on MNIST. And the reason you can see here, we're seeding it with the same random seed at every step, so it generates the same image. And the generator is learning over time to produce numbers that look real. And at the end of that, it's doing a pretty good job. We always start life with MNIST, which is great because it runs fast. It's also like the world's most boring data set. And then what happens is, like the next year, the next PhD student has the next paper using a much cooler data set. And I'll show you a couple of like the really seminal, awesome data sets. There was a question that I totally missed. Yeah.
So the generator only sees a yes/no?
The generator only sees the yes/no, and it basically has access to the discriminator's code.
Okay, so it sees the weights?
It sees the weights.
Okay.
Yeah, exactly. It sees the weights. With just a yes/no, without the weights, we need a way to get the gradient. So yeah.
How many cycles does it typically take to go from noise to a cat?
We can actually, how many cycles does it take to go to noise to a cat? So let me show you how to answer that question. And the reason that all these tutorials, they all run end to end, by the way. And we like this because you know the expression trust but verify? So they actually work, and you can find out if they don't. But if we have the output, they might have saved the output or they might not have. The output was not saved, but you can run it, and we'll find out exactly. Or I can scan through, and we can find the number of epochs that they trained this model for. But here they happen to train this for 50 epochs. Training GANs, you have to read papers. They can get into weird spaces. But here it was 50 epochs. These data sets can be surprisingly small, by the way. So in the next paper I'll show you, you can train a GAN with like 200 images, give or take. You don't need as many thousands as you would. Anyway, first GANs, let me show you how there's two neural networks at warp speed. Here's a generator, and there's more complicated layers here. We've only really briefly talked about dense. You can see there's different types of layers, right? But even though this is like clearly like a research paper, you'll notice that it's still implemented using what we call the beginner's API, which is super powerful. So this is a stack of layers, and this is one neural network, and it takes an image, and well, it produces an image. The second neural network, I talked about convolution very briefly. This is an image classifier, and it's using convolutional layers. So we talked about filters, just so you know what some of these numbers are. We talked about filters, and on the Aline Collins image, I showed you filters that were 3 by 3. These filters are 5 by 5, so they're slightly fancier filters. And this layer has 64 of those filters. So it's going to learn to detect 64 things that you can represent in 5 by 5 grids of numbers. The reason that convolution is really powerful, by the way, and I stole these slides from a friend of mine, Martin Gorner, at work. He's great. Like, they're epic, so I didn't want to redraw them. So this is an RGB image. And when we do convolution, I showed you in 2D, but convolution works in 3D. So here we have a filter, a three-dimensional filter. And in the same way that we convolved over Aline, we can convolve over a three-dimensional image with the 3D filter. And we get an output image. And what's cool is if we have a second filter, we get a second output image. And the first output image could be all the edges. This could be a different type of edge that the filters learn to detect. But the insight here is that with 4 filters, or n filters, we get n output images. So when you see, too many tabs. When you see this could take some time. When you see this, this also means there's going to be 64 output images. The really interesting thing about convolution is when we get to the next layer. So this is a 5 by 5 filter, but you see here our filter looked through this 3-dimensional space. The filters that are looking at this layer would look through a 4-dimensional space. And the filters in this code, as written, are going to look through a 64-dimensional space. So what this means is these filters are 5 by 5 by 64. So they're extremely powerful, and they're not something that we could ever write by hand. But they can detect things, who knows what you can detect by looking at 64 other images at once. So they're extremely powerful, but they're also very efficient. And that's why this doesn't have to be very deep to be very powerful. A common mistake people make too when they start with deep learning is we learned that deeper networks are better. So you have like a 20-layer network. And some types of networks, like convolutional networks, can benefit from being very deep. So like a production image classifier might have 100 layers, give or take. There's other types of layers that we use for text, and those layers are called RNNs. And there's one type of layer is an LSTM. there's no way to know the answer to this question, but let me just throw it out there anyway. So if I told you that for like that toy neural network Inception has like 20 or 30 layers, how many layers do you think Google Translate has? And the layers are called LSTMs, and Google Translate is trained on one of the world's largest data sets. So how big do you think the model is in terms of number of layers? 64?
No, 16.
16? You're actually very close.
Yeah, I know.
Yeah, you're extremely close. So surprisingly, it's almost nothing. So it happens to be 2 models. One's an encoder, or in 2014 it was 2 models. One has 7 LSTMs and the other one has 7 LSTMs. So it's 2 7-layer deep networks, which means you could literally write the thing in like 8 or 9 lines of code adding the pre-processing. So small models can be extremely powerful. Yeah? How is the text stored? Great question. How is the text stored? I will show you in the next example how to write a mini version of Google Translate. Or at least to give you the code and you can play with it. Anyway, that's a simple GAN. There's another more complicated GAN that we have code for you can try. This is from Berkeley called Pix2Pix. And here, the GAN actually starts by taking an input images. It takes an image as input. With the generator, we just say, generator, please generate me an image. Have a good time. Here we say, Pix2Pix generator, here's an input image. Generate me the corresponding output image. And this is a data set called Facades from Prague. I always forget. OK, the Czech Technical University in Prague. Anyway, the input image in Pix2Pix is a building facade. Here's the image from the training set, and here's what it manages to output, which is really beautiful. And so this, you can run this code and do exactly this. And what's cool about Pix2Pix is it just takes paired images as input. So you can do this. A common thing you can do is if you have Google Maps, you can click satellite. You now have the same region as satellite, so you can train Pix2Pix to go from map to satellite, which is really cool. So Pix2Pix is beautiful and it's amazing. And there's the complete code. Again, if you want the code, ignore things that are not in alpha, maybe beta, because it's much harder. And then the latest model, which we don't quite have code for yet, but we will in a couple weeks, is called CycleGAN, also from Berkeley. And CycleGAN does something nuts. So this is a really big deal. And so the reason this is a big deal is there is no way to collect a data set to transform images from horses to zebras, because the data set doesn't exist, right? Not found in nature. But CycleGAN can do it. And the trick to CycleGAN is, although there isn't a data set for horse to zebras, so Pix2Pix is paired, right? Meaning that you have to have input image, output image in your training set. CycleGAN takes directory of input images, directory of output images. So here's a set of horses and a set of zebras. And it can exploit supervision at the level of sets. But anyway, the paper's great. It can also do really trippy things like this, summer to winter, day to night. It's nuts. You can also convert between different artists. And again, like, there's no way to collect a data set for that. You can do photographs to artists. It's great. So CycleGAN is beautiful. Anyway, a couple weeks and we should have it done. Other amazing, continuing like the warp speed tour of amazing things you can do. Let's do like warp speed machine translation. So hopefully this doesn't go to Sephora, but bit.ly/minimal-nmt. And that stands for neural machine translation. And this is supposed to be like the fastest possible way to train a translation model using something that's not terrible. So this code should run in about a minute. And the input data, to answer your question, here's the input data to our machine translation model. And the only input data is just a corpus. And this is paired, so it's a sentence in English and a sentence in Spanish. And there's nothing in this code that knows anything about English or Spanish. So you can just modify this for English to French, or anything else you can represent in ASCII. Because you could do non-ASCII characters too, but my pre-processing code is ASCII only just to make it fast. Yeah? Oh, is this a public data set? Yes, because the code's Apache 2 on my GitHub repo. But this is just some random sentences that I stole from, I don't know. But yes, this is public. And this won't generalize. The goal of this example is just train fast, prove the point. And we have fancier examples on the website that will train in a couple hours that are much better. But the insight with, and I don't have a diagram for this, so I'm just going to tell you. One of the approaches that, and I'm also not a linguist. If anyone's a linguist, you'll know a lot more about this than me, and it's really interesting. One old approach to machine translation was you take your sentence in English, you map it to a logical form, like some form or code that you come up with that captures the meaning of the sentence. Then you have your code that gives you the meaning. Then you write a separate program that takes the meaning and emits text in whatever language you want. And this is called a interlingual representation. Like that means logic that captures the meaning. This is super hard, right? And it didn't work. Like it's not understood how we can manually write code to extract the meaning from a sentence. But it'd be great if we could. And as it turns out, the way the deep learning models work is they do exactly that. And the way that machine translation works is there's two models. There's a model called an encoder, which you're seeing here. And an encoder takes a sentence in English, or whatever's in your training set, and it maps it to a vector, which is a list of numbers. So the output of this is a list of numbers that captures roughly the meaning of the sentence. Then there's a second neural network called a decoder, which takes that list of numbers and then it emits a sentence in the target language. And in the same way that when we trained an image classifier, as we saw in Deep Dream, as an artifact, we got all these amazing filters that can detect different really abstract things. As an artifact of training this encoder-decoder model, we get an interlingual representation for free. And the reason I'm mentioning this is that like, if you happen to be a linguist, beyond the fact that we can train a machine translation model, which is awesome, there might be some value in investigating how this thing compresses sentences into a vector, because that's also really, really cool. And now we're doing research, which may or may not be useful, but that could be a cool topic to look into. Yeah. So anyway, you can read papers. Did I link to a paper for this, or did I fail to? OK, I failed to link to the paper. But if you search for like the Google Translate paper, this is like roughly how that will work.
Is the size of the vector smaller or larger than the...
Great question. Is the size of the vector that we compress this to larger or smaller? It's almost always smaller. But sadly, here it's a parameter. And unfortunately, deep learning is super experimental. So like, what's the right size for the embedding? In the same way that how big should your layers be, you find out experimentally, we find out experimentally. So deep learning is really hacky right now. And it's hacky because it's new. And so best practices we're kind of figuring out as we go. I'm going to, all right, more awesome things you can do. Let me do just two more, and then I'll stop. I'm not going to say anything about this except point you to code. Another cool thing that you can do with encoder-decoder models is you can, instead of going text to text, you can go images to text. You could also go text to images if you wanted. And so here we have a picture, and the task is to learn how to caption the picture. And so here it's an encoder model, and the difference is the encoder is a CNN. It looks almost identical to an image classifier. So the encoder model is written in a strange way here. But the encoder model is basically an image classifier, and the generator model is basically an RNN. But I'm just showing you this so you know it's a thing. Image captioning is one of these amazing things you can do. And let me show you just the last thing I want to show you, and then I'll stop a little bit early, is the only thing in TensorFlow 2 that's not like standard Python-y is this. And it's just one line. So here's some code that we've written in Python. I have some layer that I just wrote, doesn't matter. We're making some data, and we're going to call the layer on the data. And I don't care about the output. I just want to know how long this takes to run. And so if I run this in this, non-repeatable benchmark, it takes it takes 3/100ths of a second. Great. So how do we make this faster? The reason that we care about speed, so TensorFlow is a C++ backend and a Python front end. Python's easy to write, but it's super slow. And it can be about 100 times slower than C when you're multiplying matrices. So it's really slow. So when you use TensorFlow normally, it takes your Python code, and it actually does the math in C, and then returns the result. And NumPy does exactly the same thing. In addition to NumPy, TensorFlow works on GPUs, which is great. But it can do something else. And the problem is in NumPy, you're doing this round trip from Python to C, and you're ping-ponging back and forth, which is slow. But we can actually compile this code so the whole thing runs in C, and it gives us the result once. And this eliminates the round trip. And because we're compiling it in C, I'm not a compiler's engineer, but if you're compiling code and you're a compiler's guy or girl, there's all sorts of things you can do to make the code go faster. Here's how we compile the code in TensorFlow. So I'll just flip back and forth so you can see it. We just add that annotation at the top, which is TF function. And what this does is it tells the C++ backend to analyze this code, compile it, run it, and then give us the result. And if you never write this in your TensorFlow life, this only works in TensorFlow 2. Your code will work identically, and it's fine. You don't have to care about this unless you feel like it. If you want to play with making your code faster, you can do that. And by adding this function, this runs about 9 times faster, which is really cool.
Why is it just not default?
Why is it not default? Excellent question. When it's compiled, it's harder to debug. So if we get an error now, it's going to be funky. Really good question. So what you do is typically you'll write and run your code, you'll train your model, you make sure it works. When you're happy with it, you can add TF function. When you're debugging here, you can use the Python debugger. When you're debugging here, you get weird stack traces. So, but it's great. You don't always get speed ups. This can actually make your code slower because it's still being developed. It depends on the type of code you're running. Yeah.
Can you put Python control flow inside of
Great question. Can you put Python control flow? Yes, you can. So here's just some function. I stole this slide from somebody. This is out of my area. Here's Python control flow. And yes, you can. Just to say ballpark how this works, under the hood, we have a giant guide on this. It uses something called autograph. And I mentioned that TensorFlow is this graph execution engine. What it does is it's a Python source-to-source code transformer. And it rewrites your Python code. You can see what it generates, but you never have to care about this. It rewrites your Python code to look like this. And this code is in a form that the backend can compile and accelerate. So there's, yeah, that's sort of the magic under it. Typically, in practice, you don't put this in every function. What you usually do, I can just show you if I just pull up pix to pix, you can see how this works in practice. Yeah. You usually just wrap your entire training loop. So here's our training loop for the model. After you debug it, you can just put TF function on the top of the training loop. But your mileage may vary, but it looks super, super cool. So that's TF function. All right, so I will stop there. Let me give you a slide with learning resources. By the way, it went fast, but what you can do is for all the links, you can try them at home. And basically, the best way to learn it is to play with the code and just modify it. Why is this slide all screwed up? All right, so learning books, and then I will stop. Books. All right, so all the tutorials you want are at tensorflow.org/alpha, possibly /beta tomorrow, who knows. The best book, if you want a non-academic book that teaches you how to do stuff, the best book, in my opinion, is Deep Learning with Python. It's like $40. It's written in a library called Keras, but TensorFlow 2 is based on Keras, so all that code will work in TensorFlow 2 just by changing an import, no other changes, which is great. And then there's 2 courses, one from MIT and one from Stanford. Yeah, so thanks very much. And then, yeah.